Okay, hello, welcome everyone. Welcome to this session. Today we are going to talk a little bit about Java concurrency from the trenches. You might ask why from the trenches, why I pick like this particular word. The reason being because this talk is based on my own learnings through a project that I did through the last year. So everything I'm going to be talking here is based on a project that I worked through the last year until now at Netflix. But before you guys join me on that journey, let's talk a little bit about who am I? I have been 20 years Dungeons & Dragons Dungeon Master, but unfortunately, or fortunately for some of you, we are not here to talk about Dungeons & Dragons. Yeah, disappointing, I know. But on my free time, I have also been a software engineer for I think the last 15 years-ish, which most of the time I have spent on known companies such as Amazon, AWS, Twitter, and currently working at Netflix. One interesting fact is that even though I worked on all these companies in some platform engineering teams, search infrastructures, code reviews, things like that, most of the time I consider myself a product developer. I am not a performance engineer. I am not like a JVM engineer, so I don't have actually deep expertise on those topics. And you are going to notice why this is important for this talk. Another interesting fact is that I didn't have to deal with the complexities of concurrency for most of the time. Most of the time, I was just like doing my application and then my Spring framework was take care of the threads for me, was take care of all of that until it couldn't. So in this project I had actually to learn a little bit about concurrency myself and try to do some experiments and learn the things the hard way. So I'm actually here to share those learnings and mistakes. So first of all, who is this talk for? I think that if you're writing concurrent code in Java, I think this talk is for you. What I expect to happen is that you're going to either see similar issues that you faced, or you are going to see issues that I face that I hope you're not going to face anymore. So that's my goal. The other thing is that if you're dealing with scale, especially if you're dealing with I/O, this talk is also for you because our problem is mainly I/O bound problem, and I'm going to talk a little bit about that later. And finally, if you are not a Java developer, but you like to deal, you are curious about concurrency problems, and you are interested about the problem solutions, things like that, or you are here just to make fun about how we Java developers try to solve those problems, I think this talk is also for you. What this talk is not about. This is not a benchmark or a performance deep dive. Even though I did some comparisons, I did some experiments, I have metrics to show here, they are mainly to inform my decisions and to make what I was thinking at the moment that I made that decision. This is not like actually deep dive performance talk. I will also not cover JVM or low-level app tuning. This is not a talk about that. Like I mentioned, I do not come from a background of performance engineering, and I think there are a lot of great talks about that. I have some of those talks actually in the references. And finally, this is not a full reference of the Java concurrency API. Like the API is super extensive. I could not cover everything in 1 hour. And the way I'm actually using API is as a tool to solve my problem. So I'm just going to go through the small bits that I actually try to use to solve that. So first, let's start talking about some of the foundations so we have a common ground about understanding concurrency, right? The first thing I want to talk is about the difference between sequential, parallel, and concurrent code. Sequential is pretty straightforward, right? You have your CPU, and it's going to execute your task, and you have to execute finish all your task 1 before it goes to execute your task 2. When you have parallel, things start to become a little bit more interesting because now you have multiple CPUs or multiple machines, let's say, and you can execute those tasks actually at the same time. Concurrency is a funny one because concurrency, it gives you the impression that it's actually being executed at the same time, but actually what's actually happening is that it's just jumping pretty quickly between your tasks, and you think that it's actually being executed at the same time, but it's actually not. It's just switching super quickly, and that's how it goes. The other interesting concept is synchronous versus asynchronous. And when you have the synchronous code, like you have your process A executing something, it calls your process B, process A is gonna wait. It's gonna wait until you get the response back from process B. And you can see that it's gonna wait all the way from the response and then it continues executing. And finally, when you have like the asynchronous code, it's actually quite different. Process A sends the request and continues doing some work. It's actually doing some work, and later on, when it needs the response from process B, it's gonna ask process B, hey, do you have the response ready for me? And we are gonna use these a lot today. And I think this is probably one of the most important concepts here, which is like the CPU bound versus IO bound. When you have CPU bound problems, this is actually things that depend on your CPU, your cores, your machine. Like think about doing math, doing compression, like doing those loops and doing transformations and things like that. And IO bound is actually when you are waiting on network, writing to files, calling your database, anything that's related to that is going to be IO bound. This difference between CPU-bound problems versus IO-bound problems is actually going to be helpful to inform some of our decisions today. And what is the toolbox that Java gives us actually to attack some of these problems? The first thing that we have is the old good thread. Like this is very old school, and even though it's the foundation on everything is built on today, rarely we actually manipulate threads per se, like by hand. Instead, most of the time, we're actually using a thing called the executor service, which is basically working as a thread pool. Threads are expensive to be created until the new thing that I'm going to talk. But most of the time, like you are actually going to use the executor service to create your threads or give you threads that already exist. The other thing is CompletableFuture, which is kind of like, if you are coming from a JavaScript background, it's the similar thing to promises. We Java developers don't want to say that we copy JavaScript, so we decide to call this CompletableFuture. But the idea is the same. This is our way of doing like async code. So we do something, ask to be executed, and later on we are going to try to get the response. One new thing, actually not super new, is because this is around since Java 8, is parallel streams. This is kind of an easy way for you to kind of try to do parallel when you're processing streams in Java. And the new shiny kid in the block is virtual threads. I said before that threads are expensive, not with virtual threads. So the idea with virtual threads they're pretty cheap. You create virtual threads, you destroy virtual threads. You don't have to keep a pool for them. They're pretty good for I/O heavy flows, and I'm gonna like talk a little bit about them today. So let's talk a little bit about what was my problem. One thing to keep in mind though is that I changed the domain a little bit, but keep in mind this was a real problem. The traffic pattern, the code, everything else is the same. I just changed some names around. So we have a scheduler, a job. This is not your application that's actually getting requests. It's actually a cron job that runs once every 30 minutes. And that job has to process 10 regions in the planet. Each region, we are processing like somewhat around 10K orders. And for every order, we have to process somewhat like 5K products. We do gRPC calls, one call for every 100 products. And if we want to think about the scale of this, is that in the end we have to resolve somewhat around 207K RPS, requests per second, of products that we have to solve. Or if you look at the number of the batches, it's actually 2.7K. And this is only if I'm looking, you might think, oh, okay, 2.7K RPS, that's not super high. But yeah, that's only if I am actually distributing the load equally in 30 minutes, which most of the time, that's not the case. And of course, keep in mind that as I keep adding regions or I keep getting orders, this problem just goes up. And our code architecture is pretty simple, actually. I have my job. It is going to run my regions. My regions are going to call my order service. Think of this block is kind of a Java class. And then I'm going to have a products sort of class that's going to like be a proxy for my gRPC. And it's going to call gRPC one time for every 100 products. After all this is done, it comes all the way back onto my job. aggregates everything, and I'm going to write the output result. You might ask, oh, why are you not doing this for events, or why you have to get everything and write in the end? Let's abstract those details. Just keep in mind that it needs to be written at once in this file. So our first solution, or my first instinct, was like, I'm going to go simple, and I'm going to start writing a sequential code. It's going to be pretty straightforward, right? I have my regions. I go do a loop over them. I go to my order. I group them in my products in hundreds. And then later on, I start doing my gRPC calls on my products. So pretty easy, straightforward, like a couple of lines of code. You can solve this. It works. Like the code's correct. It's doing what I expect to do. It's pretty easy to understand. I could talk about this in 10 seconds, right? Is memory safe? You are not sharing state between multiple threads, and don't have other things like try to access the same resource and corrupting your data. It's pretty safe to your dependencies. You only have one thread calling your dependency at a time, so there's a good chance that you are not going to overload another service. However, it's pretty slow. I think the first time I run this, I did not have the patience to wait actually the job to finish. It underutilize your resources. Imagine that if you are in a machine that has 8 cores, you are actually only using one of those cores. You have 7 other cores that are doing nothing, just waiting there. And I felt that if I keep waiting like that, I would be just like this lady, waiting until my job was done. So I thought that, okay, we have to do something. So my first idea was like, okay, let me look at the CPU-bound problems that I have and how I can attack those problems. And to help me there, I decided to use parallel streams. Why parallel streams? Because by default, parallel streams are a one-line code change. They are pretty easy for me to go and introduce there. And for example, I have this list here. If I do a parallel stream of that, the output, you can see that's is gonna run automatically in multiple threads. So it's like minimal change is gonna run in multiple threads. So I decided, okay, easy win for me. And why CPU bound? Because parallel streams, they actually the default common pool that parallel streams are gonna use is based on the number of processors that you have. So it doesn't matter it doesn't matter if you want to say, okay, I'm gonna execute this in a fork join pool that's bigger than the number of processors, because the common one is the number of processors. So it's like, okay, I want to use all my 8 cores, so I'm gonna start using parallel streams. You can actually, like I mentioned, customize your fork join pool. For some cases, you might want more than the number of processors that you have. I have done this in the past for writing a script of some sort. Once I think I wrote something like this. But most of the time, you don't do that. You just use the default parallel streams. You can also pass a JVM argument and say, hey, I want my parallel streams to run with this number of threads. That's actually different. Just be careful, because you are changing the common fork join pool for all the libraries that are actually using a parallel stream. And you are going to see, actually in the presentation down the road, there is a library that's actually using the fork join pool. And if you're doing this here, you might impact some libraries that you do not want to impact. So one place that I noticed that I could actually try to do that was when in the beginning of when I was trying to process my regions. I decided, okay, I'm actually reading the data, and I have to parse the data, validate this data, do some regions. There is no call. It's everything on my machine. So I think this can be done as basically CPU bound. I can do that a little bit with parallel streams, and raw data is actually pretty big. So it looks like a good candidate for us to try to parallel, right? And here is where our battle begins, because this is the first of a series of mistakes that I started to do. So let's see how it goes. The first thing is that when I started to do my parallel streams, I got greedy. And I decided I want to parallelize everything. I decided, okay, I'm going to put parallel streams everywhere because I'm going to go super fast, blasting fast. So I had my first loop. And then on my toRegion method, I had another loop. So I was like, okay, another parallel stream. And imagine that you have on parse on validate loops, you put more parallel streams because more is faster, right? Not actually, because remember that your parallel streams, they run in one limited resource, which is the number of your cores, your CPUs. And now you have 2 types of tasks being created going to the fork join pool, right? And now there's more context switches for you to do. There's more tasks going on that particular queue, more things accumulating in memory. And I actually did some benchmarks, and it's actually pretty interesting that for low numbers, if you only have like a single line of parallel stream, it's actually faster. For high numbers, if you look at the benchmark, it gives you the impression that it's going to be faster if you have the nested, but when you look at what does the name? If you look at the difference, like okay, what's the max and what's the minimum of the graph, you see that's actually going to fluctuate a lot, and that's because it's like allocating a lot of objects and doing a lot of context switches. So the decision here to avoid this problem is actually parallelize where it matters the most. My raw data is actually the source of all the data, like where I have most of my objects. So I want each one of these transformations to run in a thread. So for each object of my raw data, that's actually where I'm going to parallelize. So try to focus your parallel stream where you think is going to cause most impact and try to avoid nesting. The second thing that happened to me was another interesting finding. I don't remember what I was doing, but at some point I had a flat map transformation. And I decided, again, I'm going to probably use more parallel streams everywhere. This is good. So I decided to put a parallel stream inside a flat map transformation. And then I noticed that my code was going pretty slow, and I was like, what's happening? So I added one line of code to actually print the thread name. And I realized that was actually not running parallel at all. And then I went to talk with my fellow Brazilian devs at Twitter. And then after some discussions, we discovered that the code actually, the OpenJDK for flat map transforms the stream you're passing to the flat map operation into sequential code. So it doesn't matter if you pass a parallel stream to a flat map operation, that's going to run sequential. I do not know the details about that, why this is done, but there is an extensive answer on Stack Overflow if you guys are curious about. I put those in the references. You can go take a look about why this is done. And the answer to that was actually I realized that, hey, I can actually do just a parallel stream on the outer loop on my users, because for me, the result would be the same. But just keep in mind, I remember that on the Stack Overflow answer, there is actually a workaround to go around this that does not involve you to put on the outer loop. So I think I recommend going to that particular answer. And the last thing I want to share about my learnings with parallel stream is that you have to be careful when you are dealing with thread context in parallel streams. You can see on this first line of code that I'm setting the context to be user 123, and later on I go through the loop or running on streams, and I'm trying to grab that particular context. If we execute this code, you're going to see that for all my fork join pull threads, the context is actually null. Only on the main thread, I get the context. There are two things here. One, you might be asking, okay, why you are getting the main thread? The main thread actually, when you are executing something, the fork join pull tries to get the invoking thread to actually be part of the pull itself to do the work. So that's why main thread is actually running here. It's the only thread that has access to the context. All the other threads, they do not have access to the context at all. So if you're like my company, like Netflix, we do a lot of things saving the context, request information, authentication between services, and things like that. You cannot do that from inside of parallel stream. For that, you'll probably have to use a custom executor or a custom pull or some other thing like that. And now, that solves my CPU bound problem. But as I have seen, the bulk of my problem is actually IO bound. I'm talking to a gRPC service, and I'm doing 270K calls to that. So to solve that, I decided to use a combination of executors and CompletableFutures. Executors recap, user or thread pools, and CompletableFutures is a way for me to go grab the answers when I have them. The old good Java way of creating executors is just calling these methods that are or factory methods. On this first one, I'm creating a thread pool of 4 threads. The second one, the new cache thread pool, I'm creating a thread pool that as much as I have work, new threads are going to be created, or it's going to try to reuse threads that are idle. And the last one is our single thread executor that only creates with a single thread. It's actually pretty useful if you're doing testing. I like to use that a lot. And The way you use them with CompletableFuture is you can just pass CompletableFuture supply async, your task, and you pass the executor that we want to use. This is the plain old Java way of doing it. If you are doing in Spring, you can create then a bin as a bin, and you can inject then directly on your component, and you can just do the same thing, CompletableFuture supply async or run async if you want to. This is the Spring way, option 1. Another way of actually using it with Spring is that you can annotate a method with @async and just pass the qualifier of the executor you want to run. So this here, fetch async, behaves the same way as if I call this method, this CompletableFuture supply async, passing my method. So it's kind of just syntax sugar to go around not having to write CompletableFuture supply async. And and one thing, for that to work, you have actually to do that at enable async. So you have to do that when you are starting your Spring application. The last thing about Spring is that actually Spring has a default executor by itself, and you can configure that on your application YAML. And how do you use that default executor? You just call @async in a method. You don't pass the qualifier. Automatically, that's gonna be you are gonna be using the default executor. We are gonna use down the road when you're dealing with virtual threads. So now my solution is gonna be it's something along the lines of, okay, I'm gonna loop through all my orders, right? And I'm gonna pass them to be executed in a CompletableFuture. And then later on, when I call the orders and I do the gRPC calls, when I get the response back, I'm gonna process those responses back at my executor. And this is gonna work, my code is gonna fly because I'm not gonna block anymore. And this is what I thought is what's gonna happen. I was like, okay, that's in the stars now. But actually, this is actually what happened. This was my first experience dealing with this code. And what happened? What went wrong? This was my first out of memory. And if I'm saying first, I'm already giving a spoiler that this is the first out of many. What happened here? So when I started doing this code, you can see something that I did. I did my executor when I was actually queuing the work, and I did use my executor when I was receiving some responses back. To put that in our heads in the model is almost like my region services and queuing tasks, the blue ones, to my executor. And when I call my gRPC service, I get a response back. I'm queuing the red tasks to my executor as well. The problem here is that the red ones that are arriving, they are going to the end of the queue. And my response objects are way larger than my request objects. So they just keep accumulating because my thread pool is actually trying to deal with my request tasks. And then it just blow up. I just run out of memory. And this actually illustrates the problem a little bit better. Like, as I keep getting the red tasks, they just keep going to the end of the queue. As I'm still in the middle of the queue trying to process all the blue ones, and it explodes. A quick way to solve this is actually like you can split the queues. Like you actually allocate a thread pool to deal with every particular job. So you have a thread pool to deal with your requests. You have another thread pool to deal with your responses. And if you look like, hey, why is that the gRPC default executor? Yes, because when I'm processing the responses back, I realize that, hey, I get these responses, they are actually pretty lightweight and fast to be processed. I can just use the default gRPC default executor that I already have at hand, and that's going to be processing my responses. And how do I do that? Well, the first way to do that is actually like to use the gRPC default executor, instead of doing a then apply async, I'm gonna do a then apply. Because CompletableFutures, they have these 3 versions of the code of all the APIs. They even have a then apply async where you don't pass executor, or a then apply async where you pass executor. So it's got 3 flavors. The then apply is actually gonna run the code in the thread that was running in the previous stage. If you remember, my previous stage was actually dealing with handling my gRPC response, so that was the gRPC default executor. So that's why I use the then apply. You can also solve the problem with the then apply async, the default one, and this default one is actually gonna run in your fork join pool, the same pool that I said in the beginning to not mess up with the JVM because it's going to affect things like this. And finally, you can also do with the then apply async executor, but different from what I did initially, you do not specify the same executor. Please specify a different executor. I call this one the response executor. if we look at a comparison between them, like I said, it's going to run this, then apply is going to run at the same thread as the previous stage, then apply sync at the fork join pool, the other one in the executor you pass. In terms of performance, then apply is actually faster because you are not submitting new tasks, you are just keeping the same thread that's already running. There is no context switch or things like that. And the other two are slower, just for the fact of doing context switches and things like that. The flexibility of the then apply is actually low. So the thing is, sometimes you do not know exactly what was the thread that was handling the previous stage. So sometimes it might happen that you have a chain of completable futures that arrive on your direction. You do not know the thread. So you cannot change that. If you just do a then apply, that's not going to be changeable. So then the flexibility of dealing with that is sort of low. The then apply asyncs gets more flexibility, and that's the trade-off. The trade-off is that with the then apply asyncs, you know what threads and what thread pool is going to execute your code. But you are paying for performance. That's your trade-off. And they are inverse in terms of simplicity. And one interesting thing is that the context is preserved if you use then apply, because as you keep coming in the chain, if that chain has a context in that particular thread, that means the other threads that keep doing the then apply operations, they are going to keep using the same context. When you do the then apply sync, remember, it can go to any thread. It can fall into a thread that has a context, and it might be the context that you want, or it might be a totally different thread. However, there are still problems. And this is the face of my colleagues at Netflix when they saw me calling their services with 30K RPS as fast as I could. They came to me and said, "Hey man, what are you doing here?" And that's the thing, that my app was running fine for me. But when you look at the entire system, it was actually causing then a DDoS. And how do you solve this? The thing that you have to self-throttle. You have to hey, I have to slow now. Remember when I said that I want to do a smooth traffic? That's what you want to do. And you can, on my case, I thought that I could use two mechanisms here. One was Semaphores, where I'm gonna give you a permit, and when let's say I'm gonna give 50 permits at a time, and then that means I only have 50 tasks executing at a time. And every time one of these tasks is done, when it's completed, I release the semaphore so another task can go and get in flight. Or I can do a rate limiter. That's a little bit different. That's going to say, hey, I want to do X many permits per second. In my particular case, that's the one I use because I want to protect their services to say, hey, I'm going to only allow 3,000 requests per second. And that's the rate limiter I use. Sometimes you might need both, but comparing them, the semaphore is going to control the number of concurrent calls you have, is the number of calls in flight, while the rate limiter is going to control your call frequency. The measures the semaphore is going to be the number of in-flights, while the rate limiter is the number of tasks that you start per second. Semaphore is more about protecting your own resources. You only want to keep X many things in flight so you don't blow up, let's say, my memory. And the rate limiter is about protecting your dependency. You don't want to overload them with too many tasks. Semaphores are actually really good if you have a task that runs super long. Imagine that you have a task that runs, takes 2 seconds. If you put a rate limiter that say, hey, I'm going to release 1,000 requests every second, they're going to build up. And then you are going to destroy the other service. And the risk of missing is that it's going to, the semaphore depth overloads itself, and the rate limiter, you flood your external service. But sometimes, like this, you might need actually both of them. What happened? So I added my rate limiter now. I'm protecting my gRPC service. I'm calling only 3,000 requests per second. But remember that originally I was calling with 30K RPS. And this is what happened to my application. All the blue tasks started to accumulate in the classes before them, and then I got another out of memory, of course. So the solution for that one was actually to introduce a semaphore between, when I was creating my big tasks, between my regions and my order. I create this semaphore that says, hey, you want to submit like 50 tests at a time. That's enough for us to keep our limit at 3,000 that we want. And so we do not go below the 3,000, and we do not like keep tasks, too many tasks waiting here. So I did that first. And if we look at our solution now, we have, it started with a regions, order, prod, and gRPC. Now I have a semaphore in the middle doing like 50. I have these 3,000 requests per second that I have also to control. And this is how I feel talking about this to all of you at this moment. And this is how I actually felt talking about this in a meeting with my entire team, talking about all the levers and all the control and why I have all these thread pools and things doing like that. So one colleague of mine, he asked a very good question. Hey, Hugo, can you make this simpler? I was like, interesting question. Let me see. So I took that challenge to my heart, and I went to look at a non-blocking I/O solution. Like, can I remove the rate limiter? Can I remove the semaphore? Do the entire thing as a chain of things and do completely non-blocking, just using the completable futures. So my solution started at the top again. I do my regions, and then I start to enqueue work to my process order. Let's not look at the when complete for now. Then I go to my next layer, enqueue the work to my gRPC service, and on my product, that's when I'm actually doing the gRPC call. That gRPC call, I'm actually using the non-blocking client from gRPC, and that's gonna return me a future. And that future, I'm gonna pop up all the way to the top, so something like this. And you can see that only on the top, that's when I say, hey, when my future is complete, that's when you start writing to the file. And down there on the last line, on the top, actually, on the regions, that's when I do my join. That's actually the blocking call. So it goes all the way down, unblocking, and goes all the way up. And if you're asking me like, hey, but how are things holding up here? What's applying the back pressure? The back pressure is actually being applied by the gRPC service itself, the gRPC framework itself. We internally have some semaphores and controls on gRPC, so I was actually using those to my advantage to have one single lever to control all my concurrency. And the results of that was actually pretty good. Like, I was able to run this entire code. I think it ran in a single machine, like 22 minutes of some sort. And I was not flooding my service and everything. However, this has a problem. If you look at if you remember my sequential code in the beginning, like it was like 3 or 4 lines of code. I have all this just to deal with complexity of like completable futures and non-blocking I/O and all that stuff. Like, it becomes pretty complex and sometimes pretty hard to debug. And this is my colleague coming back to me again and say, man, I said simpler, not more complex. So I had to go back to the drawing board. Another solution that I tried is like, okay, what if instead of like using semaphores, rate limiters, and all that stuff, I tried just a bounded executor. I'm just gonna try a simple fixed thread pool that has a limit on a queue, and it's gonna not allow, instead of semaphore, I have just this queue that allow a couple of tasks. And I wrote my own like executor that says, hey, I have this array blocking queue that's gonna only allow this queue size. And the second line here in highlight is that, okay, if the queue is full, you block it. So it's basically doing the same thing that the semaphore was gonna do, but it's already embedded inside of your executor. So now the code becomes a little bit simpler. Like, you have your regions, don't have all the complexity anymore about that. And you do your orders, and finally, you remember that the async bounded executor right there, and that solution works. It's actually great, but it could be better. And how it could be better? Well, we have a new shiny kid on the block that can help us like simplify this code quite a lot and not have to deal with a lot of things like managing pools and things like that. So I decided, okay, I'm gonna give virtual threads a chance. So very quick recap, because I think we're running out of time, but like virtual threads, you have your traditional platform threads, one-to-one with your OS threads, and you have a lot of virtual threads. The virtual threads, as they keep getting blocked by your I/O, they keep getting mounted, and another virtual thread go to a platform thread to actually do the work, right? It's pretty easy to enable them with Spring. You can just say, hey, threads virtual enable true, or you can create your own executor with passing the new virtual thread executor Spring and inject them. And now, the code becomes something along these lines, like, hey, I have my regions order, I'm gonna loop through them. I'm gonna use at async, because now I'm using the default executor from Spring, and because now my default executor is a virtual thread executor, that I'm gonna create virtual threads here by default. And I'm also creating virtual threads when I'm calling my gRPC client, so I'm gonna have like 2 layers of execution there. However, again, more problems. And the first problem I faced is the first time I tried to run this was actually last year, I think around July, and we were running on Java 21. In Java 21, we have this problem with virtual threads that got to be known as the pinning problem. I think Netflix has a cool blog post about it, that we found this actually blocking a lot of our operations. Going very succinct here, what happens is that sometimes there are certain conditions that might cause your virtual thread to actually get pin on your carrier thread. It's not going to mount. So if that happens enough, it can cause problems like slowing your application. Or on my case, I actually saw this causing my application to completely stall. Like the application just stopped working. And this is a very quick code that kind of demonstrates that. Like every time your virtual thread here got into the synchronizer block, that's going to like pin your thread to the carrier thread. So this is a good demonstration of the problem. The good news are that if you're actually updating your code, there's no action, like if you're updating your JDK, you don't need to do anything to solve this problem. It's already been solved for you with JDK 24. So, and then I saw this, got super excited this year in March. I was like, oh, JDK 24 is there, I'm gonna try it. If you don't want to try 24, you can wait for 25 in September, which is gonna be the LTS version. And then when I try again, another out of memory, of course. Why? Well, if you remember what I did with the parallel streams where I got greedy, you might have seen a pattern here. And the pattern is that I also got greedy with virtual threads. I thought people told me they were lightweight, so I thought they were magical. They're going to solve all my problems. But they're not going to do that. And I created 2 nested actual virtual threads. I'm creating async at order task, and I'm also creating virtual threads at gRPC task. And you can remember that is 1 per 100, so I'm going to have a lot of those gRPC tasks being created inside of each one of these order tasks, and I have 10,000 of them, so it's a lot. So yeah, you do not simply replace your platform threads with virtual threads and just expect them to work fine. So back my semaphore to apply some back pressure and control the pace where I create virtual threads. And the code is pretty straightforward. Just before I create my supply sync, I pass that to the virtual thread, I create a semaphore. OK, and what were the results of this adventure? The first thing is that if I compare the bounded executor, which I was actually running in prod, that solution was somewhat complex but worked really well. I have 3 nodes, each one running my service at 12 minutes of execution time. And what about this solution of the semaphore with virtual threads? Ta-da, no changes, but actually worked fine. It runs in somewhat of 12 minutes. It still has its complexities. It's almost one reflection of the same. One is using the bounded executor like with a queue. The other one is using a semaphore to control the flow. And the pressure is that, OK, I'm having peaks still of 34K RPS, but my average is just an initial peak. After down, it stabilizes on 5K RPS for my bounded executor. And for my virtual threads, actually got pretty good. Like, I don't know exactly what's happening under the hood, that the peak is lower, but I got a peak of 16K RPS to my downstream service. But then I ask a question again, can I make this simpler? If I look at my metrics, I notice that one right there, that's the number of in-flight requests that I have to my gRPC service. The max is 70. The number low here is going to be something around 40. So I said, OK, maybe if I have 50 requests at a time, I'm going to get a very steady traffic to my downstream service. How I can get 50 requests with virtual threads and keep my code even simpler? The solution for that was actually to remove the inner gRPC, the inner virtual thread from all my tasks and focus on running the entire block, the order task, one at a time. So it's going to run all this code that inside of the virtual thread just sequentially. So it's going to call each one of those calls to the gRPC sequentially, but it's going to have a lot of other tasks running in parallel. How many? I want 50, so it gets easy. I just want to put as 50 here in my semaphore. And if I compare my two solutions on virtual threads, the first one I got of course control about my levers and controlling concurrency because I don't control how many products I have. So I don't have a very fine control there. This one I actually have pretty fine control. My levers here, I have two levers right now, order and gRPC level. This one I only have the lever at order level. And I have the semaphore size. That gRPC semaphore is just the internal one. I have an internal one there as well, but because the numbers are the same, I don't have to be concerned about that. The first version is better than my I/O version for sure. It's less complex, but this one is even more simpler. And if I look at the numbers for this version, even removing the internal virtual thread execution, it's still the same. Actually, faster, maybe a minute or so. And when it comes to pressure to my downstream service, I got down to 16K RPS to 13K RPS while keeping the execution time the same. And now I can finally agree with the guy, like, okay, now I have a good working solution that I can deploy. So what are key takeaways from this talk? If you go home and like you have to remember this talk and all the fun memes, what I want you guys to remember. The first thing is that you have to experiment and measure your solutions. You cannot just throw parallel and concurrency and just hope and pray that's actually going to work and going to solve all your problems. You have to measure and do some benchmarking. Sometimes you don't need to do load tests or something like that. Just being able to run your two applications side by side and compare it, look at the metrics is enough. That's actually what I did. The other thing and this was a key learning for me, I did a talk with a performance engineer from Netflix, and he told me, hey, you have to look at what you want to protect. If you keep the pattern that I was going around here is that I want to protect first my dependency service. I don't want to flood them. So I work backwards from that. What is the metric that I want to keep steady and stable? And in my case was the number of in-flight connections and my RPS. That's where I want to go. And after that, I work backwards to see how much I can extract from my own application without flooding my memory or my CPU or other resources. And the last thing is that concurrency is hard. So if you can actually like not do this and rely on your tools and plus one to virtual threads coming and help us to not have to keep dealing with a lot of like these pools, thread pools and things like that, I think that's for the best. But sometimes you're going to have to get your hands dirty. But if you do, try to keep the solution as simple as possible. Because it's easier to operate and easier to get your head around and to explain to your teammates. Yeah, so those were my learnings. All the references and things that I have researched, I share on this QR code a lot of cool talks about performance, threads, and all between. And if you guys want to talk about either threads or Dungeons & Dragons, you can also always reach out to me on each one of these social media. So yeah, that's all. Not sure if we have time. Do we have time for questions? Yes? Any questions? No. Oh, question there.
Hi, that was a great presentation. I was wondering, so it seems like your application was mostly CPU bound and IO bound. Did you encounter like memory bound issues up front, or was it only causing problems? Because sometimes, memory is quite constrained in.
No, the memory for me was mostly about like, at some point I thought the memory was going to be a problem. That I thought about, hey, okay, what if I have to increase my memory just a little bit? Maybe I'm going to get the performance I needed. But it happened that it doesn't matter how much memory I created on my virtual machine, like it was not enough. So my application was not memory bound at all. Like as soon as I got control of like the flow of the requests and how much I was using my CPU, the memory got down and got stable, and I never went like above, let's say, 50% of the usage. I was actually able to reduce the memory that I had on that virtual machine. But like if I had to approach a problem like memory bound, I would do the same kind of thing, like work backwards. Like, okay, now I have to protect this memory. How many tasks does it fit my machine? Can I run that's actually gonna fit the memory? So it becomes like almost like instead of looking at the dependency that I'm calling, now we are looking at how can I protect my machine from running out of memory. So you put that limit, you know how many tasks, and that becomes like the resource you want to protect. Question here?
Thank you for that presentation. Sorry. In each iteration, like, did you test it in production, or was like just staging?
Let's see. Some of the early ones that they run out of memory, they were in production actually, but of course before I dial up my experiment to start like actually producing the data for real. So it was running in my production machines, consuming production data, but not serving data, and like there was no dependency on me yet. Down the road, I think when I was experimenting with Async IO and with virtual threads, they're not production, but I was able to kind of like just clone production. So I had this shadow cluster running the same type of machines as production, consuming the same data as production, but like writing data to something else that I had no dependencies. And that's actually how when I show the graphs that compare bounded executor versus virtual threads, that's actually exactly what I had. Like one of those, the bounded one, is actually production. The other one is shadow production. I don't have my virtual thread deployed yet because I was like, I'm gonna go to a conference, better not deploy this. But like, I have this kind of like feature that allow me to run these clusters side by side and compare the metrics, and that was actually pretty helpful. Yeah. Okay, if there, one.
Hey, Sean from Roblox. In this test, you guys had like fairly constant, number of requests going from one service to another. Did you ever look at what would happen with scale if that were to change and that were to explode? And at any point, did you ever consider like distributing the load to multiple systems or multiple pieces of hardware and so on?
Yeah, actually, this thing here, I think that maybe is not clear down on this graph, but you see these three lines. These are actually three machines. At some point, I noticed that one machine was not going to be enough to process what I needed. So I designed my application that I could shard the load between three machines. And the way that I designed the code was actually in such a way that now if I have more traffic, if I have to run more things, the only thing I need to add is add one more node to my cluster. And then I got the scalability that I needed. So that's actually another trick that like you have to think about, okay, how can I scale my cluster horizontally so I can keep adding things and can scale my application, not only at the node level, but now at the cluster level.
I'm Fo from ClassPass. Did you ever have to take into account retries if the backend service starts erroring out or failing?
Yeah, so I did, I think there are some retries, most of the time. There is another graph that's not shown here that shows the number of retries that are happening. I take that into account just kind of to measure okay, if there are a lot of retries, maybe I'm saturating the other service. So that was one of the signals that I was looking for. Then one of the iterations that I was doing for 30K RPS, I was getting a lot of retries. And a lot of also the deadline exceeded because the service was basically dying. So I take that into account. The other thing is that for errors, for example, if I do a retry and does not fail, for this particular job, it's fine. This job can fail, and the next iteration, I'm going to pick it up. So I kind of accept failure as part of this particular design. And for retries specifically, you have to be careful, and this is a learning from my AWS times. You have just to be careful about the retries not flooding your downstream service as a consequence of the retries themselves. I would just say that. Yeah.
Thanks.
Cool. I think we're on time, but yeah. So you guys can always reach out to me down here, and we can talk more about this or Dungeons and Dragons.